In this video, we're going to explore requirements modeling. The requirements model is a set of models that make up the first technical representations of the software system you're attempting to develop. This stage of the project is particularly important to get right, as mistakes made here can impact all future parts of the project, design, and construction. You may be excited to jump into coding, but a few hours of planning and modeling can save you days of constructing the wrong thing or redoing work to correct errors, so this is important. We have spoken previously about requirements gathering and the process of collecting requirements from stakeholders. After requirements are gathered, we need to analyze and elaborate on them. Requirements analysis has three main objectives: specification of the system's operational characteristics, documentation of how the system interfaces with other system elements, and establishing constraints that the software must meet. The benefits of this process to us are more detailed and useful requirements, and models that depict various aspects of the system, including user scenarios, classes, behavior, data, and information flow. The idea here is that we have completed the communication activity, we have our requirements, and now we're starting to model these requirements into something we can use to build our software. This is very much the modeling activity. This requirements model we are developing will take us from a system-level description, that is, a description of the software's functionality, and provide us with information that can be translated into architectural, interface, and component-level designs later in the project. This analysis model acts as a bridge between the system description and our future design model. But keep in mind, we are still very much focused on the what and not the how. This should not be a technical description of the system, but rather a description of what the system is. It should answer questions such as what user interactions occur, what objects are manipulated, what functions must be performed, what behaviors must be exhibited, what interfaces are defined, and what constraints apply. As I mentioned at the start of the video, the requirements model is actually made up of multiple, smaller, more specific models. We've already taken a look at some scenario-based models in this course. These depict the functional requirements of the system from the view of the system's actors. These models can include work products such as use case diagrams, use cases, user stories, and actor and user profiles. Class-oriented models show the object-oriented classes that might be present in the system. These detail not only the attributes and operations of each class, but also the relationships between them and how they collaborate. These models are documented with work products such as UML class diagrams or Class Responsibility Collaborator, CRC, modeling. We'll talk about that second one later in this video. Behavioral modeling depicts how the software reacts to events. And we document this using UML activity diagrams, their swimline variant, or in state diagrams. We'll also talk about state diagrams in a later video. The data model tells us about the information domain of the problem we're trying to solve. The information domain encompasses areas such as databases, data architecture, data management, data analytics, information retrieval, and knowledge representation. It's effectively how our software will handle, store, process, and represent its data. One work product we might create to document this, especially if we're using a database, is an entity relationship diagram, also called an ERD. We won't be going into ERDs too much in this course, but it is something you'll run into in your database courses. And the last set of models are the flow-oriented models. These models represent the functional parts of the system and describe how they transform data. These models are often detailed in a data flow diagram, or DFDs. This week, we'll mostly be focusing on these behavioral and class-oriented models. To summarize, the ultimate goal of requirements modeling should be the creation of an analysis model that describes the system from three perspectives. The scenario-based elements of the system that we went over previously in this course are documented with use cases, use case diagrams, activity and swim lane diagrams, and sequence diagrams. Class-based elements are documented with class diagrams, CRC models, and so on. And behavioral elements captured with UML state and activity diagrams. Now you might be thinking that's a lot of work products to produce. Do I create all of them for all parts of the system or just some? How do I know which work products to create? Well, general rule is to only create models that will be used by the development team. If models developed in the requirements analysis phase are not referred to during the design and implementation phase, they may not be worth updating or creating. After completing multiple projects, your team will start to get a better feel of what work products are useful for your particular development style. Before we start getting into the details of these models, there are a few things to keep in mind, or a few rules of thumb to consider. The level of abstraction we are at is still relatively high. We should be focusing on the problem or business domain without becoming too concrete in our design or getting into technical details. The goal is to provide insight into the information domain, function, and behavior of the software, without getting too much into infrastructure or non-functional details yet. Also, it's important to keep stakeholders involved in this analysis. As such, our model should be simple and non-technical as possible to ensure they can be understood by all stakeholders, even if they don't have a technical background. Now, for the remainder of this video, we're going to talk specifically about class-based modeling. Behavioral modeling will be covered in a second video. Class-based models represent a few important details about the object-oriented classes that exist in the problem space of our software application. So what's the problem space? The problem space is the space where all your stakeholder needs exist that you would like your software solution to address. This is in contrast to the solution space, which describes how we will be specifically addressing these needs and includes technical representations of our software. Remember, we're still very much in the what, not the how phase. The difference is key here, as our current goal is to document classes in the problem space and not the solution space. Later design work will build on these to create solutions. We're currently trying to understand the problem. Getting back to class-based modeling, the first thing it represents are the objects the system will manipulate or transform, and their corresponding classes. This is also a description of the attributes these objects will provide values for. Next are the operations that will be applied to objects to perform this manipulation. These may eventually become our class's methods. We also need to represent the relationships between objects, including generalizations and realizations. These would be like the inheritance and implementation relationships that you might have in something like Java. And lastly, the collaborations that occur between the classes. And lastly, we need to represent the collaborations that occur between the classes. Collaborations here refers to the relationship between classes in which they work together to achieve a common goal. Collaboration between objects occurs when an object interacts with each other to carry out a task or process, such as calling a method, events, message passing, or so on. The first step in class-based modeling is to identify the analysis classes. So what are analysis classes? Well, analysis classes provide a clear and abstract representation of the objects and relationships in the problem space, without being concerned with implementation or technical details. Once again, the problem space refers to the area in which our particular problem exists. It is the context or scope of the problem that needs to be solved. The problem space includes all the information and elements that are relevant to the problem and must be considered when developing a solution. Again, this is in contrast to the solution space, which refers to the set of possible solutions to a particular problem with a defined problem space. The solution space includes all the options and alternatives that can be considered when developing a solution to a problem. So once again, right now we're looking at the problem space, more of what the system's going to do, what the problem is that we're trying to solve. We're not yet at the technical detail level. One of the techniques we can use to identify analysis classes is with a grammatical parse of our usage scenarios. These would be narrative descriptions of the system's function from the user's perspective, such as use cases and user stories. During this grammatical parse, we examine each scenario by underlying each noun or noun phrase and then entering them into a simple table to keep track of them. Nouns refer to a thing, person, animal, or place. We should also know any synonyms. That is, two noun words with the same meaning in our system. These nouns are potential classes that might be part of our software or help with understanding the problem. But this list of nouns on its own is not enough. We need to take a closer look to categorize them and filter out any nouns that might not actually be classes. So analysis classes manifest themselves in a few different ways that fall into one or more categories. These are those categories I mentioned when I said we have to categorize the nouns. So let's go through each category and describe it. The first category is external entities. These are things such as other systems or people that produce or consume information. The next category is things. This would be things such as reports, displays, letters, signals, and so on that are part of the information domain. Next are occurrences. These are occurrences or events that occur as a result of system operation. Next is roles. Roles such as manager, engineer, salesperson, basically roles played by people who interact with the system. Next category is organizational units, and these would be things like divisions, groups, or teams that are relevant to the application or the business. Next category is places, such as the manufacturing floor, loading dock, server room, or so on, some sort of a place that establishes context of the problem. And lastly, we have structures. These would be things like sensors, computers, or other physical objects that define a class of object or related class of objects. So let's take a look at an actual example. And this is that user narrative from the Safe Home security example we've been following in our textbook and in past lectures. It describes the process of installing, configuring, and use of the security system. So take a few minutes, read through this user narrative that I have on the screen right now, and highlight any nouns or noun phrases by underlining them, or whatever you can do that's easy for you on your computer. If you underline or highlight a noun in some way, make sure that you only do it once. You don't need to keep underlining or highlighting it a second time. So pause this timer if you need more time, and we'll be back in a few minutes. And we're back. You can now see all of the nouns or noun phrases highlighted. Note that if we highlight a word like homeowner once, we don't need to do it again the next time we see it. Each of these words could be a potential analysis class. The next step is to make a table of the potential classes and categorize them using the categories we saw previously. In some cases, a class might fall under two or more categories. For example, homeowner would be classified as both a role and an external entity. There may also be some ambiguity here that should be clarified with the stakeholder, such as whether a monitoring service is an organizational unit that's part of the system or an external entity. It can also help at this point to note if a noun is not really its own object, but an attribute of another class, such as number and type or sensor. In this example, these would be attributes of the sensor rather than their own objects, so we could rule those out right away. The next step is to filter our list and remove any nouns that shouldn't really be classes. Now, we could think about this logically, but there's also a few rules that we have here that we could use as a sort of heuristic to make this easier. So to be considered as a legitimate candidate for inclusion, potential class should satisfy most of these rules. So rule 1 is retain information. Potential class will be useful during analysis only if information about it is remembered. If the system does not need to store information about this class, it might not be useful. Rule 2 is needed services. This is very similar to Rule 1 except for operations. So potential classes must have a set of identifiable operations that can change the value of its attributes in some way. Next is Rule 3, multiple attributes. A class with a single attribute may be better represented as an attribute of another class. For example, something like phone number would be better suited as an attribute for another class rather than its own class. Rule 4, common attributes. A set of attributes can be defined for potential classes, and attributes apply to all instances of the class. Rule 5, common operations. Same idea as Rule 4, but for operations. A set of operations can be defined for the potential class, and the operations apply to all instances of the class. So Rule 4 and 5 here are just standard OOP things, and they say that everything in a class should be applicable to all the objects or instances of that class. Rule 6, essential requirements. So external entities that appear in the problem space and produce or consume information essential to the solution will usually be defined as an analysis class in the model. Okay, I know that's a lot to take in, but if we apply these heuristics to our table of potential classes, we are able to filter out a few that we don't need, at least not yet. So let's take a look. First one here, homeowner, seems like it is an important class, but based on the scenario we just read, no information is stored about them, and they don't have any identifiable operations. This violates Rule 1, retain information, and Rule 2, needed services. If each homeowner had their own username and password, then it would be a little bit different, and we might actually be worth keeping this as a class. But since we don't have any information about them that's stored, they are not really a class, at least not yet. Maybe they will be when we get to our solution space. Next up is installation. We reject this as it is more of an occurrence when the system is installed and not truly part of the system when it's running. We don't really keep information about the installation process, and we don't really do anything in the installation process, something the technician does. So both number and type fail Rule 3, as they are single attributes of another class. In this case, they would be better suited to being attributes of the sensor class. Next up are master password and telephone number, and they have the same problem as type and number. These are both single attributes that should be attributes of another class. And last is monitoring service, and it has the same issue as homeowner. The usage scenario we analyze does not specify that any information is stored about it, thus violating Rule 1. And it doesn't clearly state that it has any needed services, violating Rule 2. So these remaining classes, sensor, control panel, system, sensor event, and audible alarm, are our final candidates for analysis classes for our system. These would be the ones that we keep. So now that we know which classes we should be focusing on and which ones are part of our analysis model, what should their attributes be? Recall that attributes are some property or value that all objects belonging to this class will have a value for. For example, if we had a person class, attributes might be things like age, sex, birth date, height, and so on. In many cases, the attributes of a class might be apparent. In others, it might help to take a look at our usage scenarios again and try to identify any things that belong to our analysis class. For example, in this case, a sensor is stated to have a number and a type that belongs to it. These are hints that these are attributes in the sensor class. Next are the operations. Operations are behaviors that are common to all objects of the same class. In programming terms, these would eventually become the methods that the classes will have. So these operations can be divided into 4 general categories. Category 1 are ones that manipulate or transform data in some way. Category 2 are ones that perform a computation of some kind. Category 3 are ones that inquire about the state of the object. And lastly, we have ones that monitor an object for occurrences of an event. So operations accomplish these tasks by operating on the attributes or associations of that class. That's important to keep in mind because it tells us a little bit about where those operations should go. Can't have an operation in a class if it can't access the attributes it needs for that computation or transformation. So how do we identify these operations? Well, one potential method is to look for verbs in our usage narratives. So remember previously we looked for nouns to find classes. Now we're going to look for verbs to find operations for these classes. Now a verb is a word that indicates a physical action, such as drive, a mental action, such as think, or a state of being, such as exist. Well, verbs are a good general rule of thumb. We also want to look for anything that describes a behavior of a class that should be included. We don't want to get too bogged down in what is and isn't a verb. Remember, this isn't an English test. We're looking for things that show behaviors of a class. So I'm going to give you a few minutes again to take a look at the same narrative we saw before. Here we already have the nouns highlighted in red, but try to identify some verbs or other words that could be operations. So I'm going to put a timer up, but pause the video if you feel you need more time. After the timer's done, we'll take up the solution. Here we have the verbs and other words that might become operations highlighted in blue. Remember that just like with the nouns, these are just potential operations, or hints at what operations might exist. We still need to think critically about what classes they belong to and if they are appropriate. Let's take a look at the specific example of the system class. This is one of the analysis classes we identified earlier when we did our grammatical parse for nouns. When we describe an analysis class, the most important information to detail is the class name, list of attributes, and a list of operations. Implementation and technical details are omitted at this point. Not all required attributes and operations are listed. Attribute types, parameter types, return types, and etc. may not be listed yet. Operations may not yet have parameters listed. Visibility, public, private, protected, and so on also may not be listed. The idea here is that we don't want to provide technical solution, but we're trying to describe the problem. So there might be a lot of methods and attributes that we will actually need later, not shown. So as we start moving from analysis model to design model, which we'll cover in later lectures, that is when we will start filling in the details such as types, missing attributes, operations, parameters, returns, and so on. But for now, we're just mostly focused on what is described in those usage scenarios. So that covers classes, attributes, and operations. How do we figure out what class relationships exist in our system? Well, one way is through CRC modeling and cards. CRC stands for Class Responsibility Collaborator. The responsibility of a class refers to the specific tasks or functions that a class is responsible for performing. It represents the class's role and the specific problem that it is intended to solve. A collaborator is another class or component in the system that a class interacts with or depends on in order to fulfill its responsibilities. So CRC modeling entails the creation of index cards where each card represents a class. Each card is then divided into 3 sections that specify the name of the class, the list of the class's responsibilities, and the other classes that collaborate with this class. They look something like this. For this case, we have a class called Floor Plan, which is responsible for the following: defining a floor name and type, managing the floor plan positioning, scaling the floor plan for display, incorporating walls, doors, and windows, and showing the position of video cameras. The classes it collaborates with are wall and camera. The idea here is that you would have a card like this for each of the analysis classes you identified. So once again, to be clear, a responsibility of a class refers to the specific tasks or functions that a class is responsible for performing. These are both the attributes and operations of the class. A collaborator is another class or component in the system that a class interacts with or depends on in order to fulfill its responsibilities. This means there is some relationship with that other class, such as an association that enables the sharing of information. So one thing that I've mentioned several times so far in this course is that we should always have a review or validation step in our process to ensure our work products are as complete and error-free as possible. So it should be no surprise that the last step of class modeling is to review our work. One way we can accomplish this review is with the CR model review process. This involves calling a meeting with select stakeholders and developers and giving each person present in the meeting a subset of the CRC cards we created. Remember, the CRC cards have a card for each analysis class that we've identified, as well as its collaborators and responsibilities. So the review facilitator reads the use case we base these cards on, and as they come to a named object, they pass a token to the person with the corresponding card. The holder of the card is then asked to describe the responsibilities noted on the card. The group then determines whether the responsibilities satisfy the use case. Lastly, if an error is found, changes are made to correct the card. This may include creating new classes or revisiting the list of responsibilities or collaborators on existing cards. In theory, once we've done this for the whole use case, we should have a fairly good idea of what classes are involved and what their responsibilities and collaborators are. We would then repeat this process for each use case that we wish to review, And at the end, we should have a pretty good idea of all the analysis classes that exist in the problem space. So that's all I have for you on class modeling. The topic of requirements modeling and analysis is carried on in the next video on behavioral modeling. Make sure you also give that one a watch, as it also describes two new UML diagrams, state diagrams, and sequence diagrams. Thank you for watching, and have a great day.